Okay, I want to welcome everybody. This is Joe Armstrong and the April Power Systems Virtual User Group webinar. So I want to start with just one announcement before we get going. So next week is IBM's Power Storage TechU, Technical University, really known as TechU. So if you've heard me before, you know I think this is probably the best conference that IBM puts on. For us technical kind of people. Great sessions. There are just hundreds of sessions. I've looked through it a little bit. Great sessions to learn, some labs as well. So if you're going, feel free to try and contact me. You can text me or whatever. We can hook up. I still have a few Bug t-shirts I can give away. If you're still thinking about going and you might sign up, I have the discount code still is on the wiki. So you can go to the wiki. You can still get that early bird discount with the Bug discount code. So feel free to do that, and let me know if you can make it. And I hope to see you there, as many people as I can. So with that, let's get started for today. One, I am recording the session. So just so you know that, I guess I have to say something about, if you don't want to be recorded, you can drop. Second of all, the presentation materials for today are out on the wiki as well, so you can go out there and download those when you want to. So with that, we're kind of branching off, as I said in the note, to a little bit different topic. Today we're going to talk about one of the emerging technologies, really artificial intelligence and machine learning, deep learning type topics. So today we're going to talk about PowerAI Vision. And IBM has done a lot of work in this, and we have with us today two people who are going to kind of help us get through this topic. One is Srini Chittavelli, and Srini is the product manager for, he's the offering manager for a product manager in cognitive systems, and he leads the PowerAI Vision front to the market here. And Srini has been with IBM for 20 years, had several roles. He's a very technical person, master inventor, 12 patents to his name, real techie at heart. And we're happy to have him to talk about this. I think he'll do a great job. Following Srini, we've got Clarice Taffy-Heglin. And Clarice is an IT architect, and she helps clients define their AI strategy. She's really in the trenches working with clients on this. She works with the IBM Systems Worldwide Client Experience Center, so where she helps design client solutions. She helps with proof of concepts. And Clarice's background is in numerical analysis, parallel systems optimization. She has a Master of Science degree in mathematics for Purdue. And so Clarice is really there to help as well. Clarice is going to do a demo for us, talk about some use cases. And I have to tell you, I've worked with a few different clients on this PowerAI Vision, and it is so easy to come up with use cases for almost any industry. And so I think as we go through and we talk about this, and maybe it'll help you come up with some use cases that might be helpful for you. And this product just makes it very easy to build a model to do that. And I think as we go through this with Srini and Clarice, you'll see that. So we're going to start with Srini, and with that, Srini, I'll hand it over to you.
Thank you, Joe. Thank you very much. So, well, let's get started. So my name is Srini Chittavelli. I'm the product manager with IBM offering managers. And I lead a product, PowerAI Vision. This is a product that helps our customers to build models for computer vision, and then the model can be used by application developers to build a solution. All right, so a lot of stuff for me to show and talk about, but let me set the stage for where the industry is, what is the market opportunity, what are the use cases, and then I will try to address the problem, and then I will try to talk about how we simplify it for our customers. All right, so the numbers don't lie. Cognitive IT will grow 3 times in the coming years. It's projected to be several $billion. It's a $30 billion by IDC market. By cognitive, we mean by systems and businesses. They learn by themselves. They check on data, and then they prescribe a solution for their customers, basically, right? And this billion-dollar number is scattered across software, services, hardware, and whatnot, right? Things of different nature. So anyway, so there is market for cognitive sciences, and I'd like to focus most of my energy today on computer vision. Computer vision is a cognitive study. It's a cognitive application. Think about a machine that can understand the world around you, right? So to set the face, to set the tone, think about how you would train a machine to recognize a bicycle, right? So you would train it with a sample data set. Or think about a child, a baby. How do you teach the baby, like, hey, here's a bicycle, right? So you show different pictures in different angles, right? And things get a little bit complicated when you come across trash bicycles that don't look very common, right? And really surprise the child when you have a toilet seat as part of your bicycle. But it's still a bicycle. It takes a person from point A to point B. The point here is how do you make machines cognitive to an object, right? And that's called computer vision. I'm very sure that our audience on the call today has seen a version of this particular slide that talks about artificial intelligence, machine learning, deep learning. And you might have heard about its various narrations. I will try to explain this in my word. I'm trying to set the stage for what you will see in the next 15 minutes. All right. So artificial intelligence, think about this as an application. If you have a smartwatch and the watch is waking you up at 6 a.m. and you haven't trained it or you haven't tuned it or configured it or set an alarm, that's artificial intelligence. The watch is monitoring your pulse rate or maybe your movement and figures out, yep, this is the time Srini wakes up every day. That's an application. That's an artificial application. Now, how do you make an artificial intelligence, an application smart, right? So there are a couple of ways to do it. Machine learning and deep learning are the broader names for the underlying sciences. But machine learning is an art where both of these technologies are based off training data set, historical data set. You need to train machines based on the past activities, create features, and then train the model so that it can start inferring on new real-time data. And deep learning is a science where the models mimic human brains. If you think about human brains with several neurons, each neuron connected to a different neuron by synapses, each neuron knows a little bit of the picture that comes in, a little bit of information that comes into the system, right? It could be smell, it could be voice, audio, or it could be vision, right? So that's deep learning. But the beauty is, with deep learning, the more the data, the more accurate the models become. All right, so I have one more slide on differentiating between machine learning and deep learning, right? On the far left side, if you have to train a model to detect a stapler, right? In machine learning, you will have to bank on technical resources who can define the features of this object called a stapler, all right? It's got a flat bottom. It's got a sharp edge. It could have a rounded top, right? And you would want to pull in data that resembles that feature, and you would want to train that model as a stapler. The point here is you still need a technical resource who understands, who can code in the features of that stapler. But with deep learning, the system learns by data set. The system self-extracts these features and assigns, hey, what is this stapler looking like, right? So even if you threw in a stapler with a round bottom or a sharp top, it could still say that it's a stapler because the neural network derived these features without a data scientist or without a technical person. But you still need a data scientist to define the best neural network. Is this a fast RCN network, or is it a mass RCN, or it's a Google right? So not all networks are created equal. So you still need a data scientist to define this network, to define the hyperparameters or the weights between each node. You still need a data scientist, but at least this is deep learning. The science is more data driven than feature extraction. All right. So let's move on to the words that we hear, right? Deep learning, machine learning. It's not in the previous charts. I emphasized that deep learning is a technology that learns by data set, training data set as we call them, and it's actually increases as the data sets try to increase. Right? On the machine learning side, it tapers off because somebody has defined a fixed set of features for that particular challenge. Right? If you have to introduce or if you have to train a model that will detect a car that had wings, you need to bring in a technical person to define the features of the car with the wings and then try to retrain it, right? So on traditional machine learning, the system tapers off because it's limited to the number of features defined for that model. So it's not continuous without an interruption. Now, is deep learning a buzzword? It's not, right? It's definitely not. If you did a search, Google search on deep learning and looked at these trends, it has gone off the charts since early 2011, right? A lot of cool things happened since 2008, since NVIDIA introduced their GPUs for mainstream computing. They moved away, they extended their GPUs from gaming to mainstream. And I believe in 2011, in one of the Kaggle competitions, GPUs were used to train models on ImageNet data sets with fantastic error rates as low as, I believe, 3%. That means a human can see has an error rate of 5%, and machines can now beat that, right? If there's a far object which is blurred out, machines can identify better than humans without help. Okay. So deep learning is not a buzzword. It is growing. Companies are trying to embrace this new technology to transform their businesses. All right. So now we will jump into the different use cases that we come across that we help our customers to develop. Okay. I will show a few things in different domains. Here is a use case in retail. On the left side, you see a shelf with products, shelf half empty, right? The idea here is for cameras to capture the details on the shelf and then shout out to the supervisor to bring in more Diet Cokes or Coke cans or fill up the shelf, right? On the far right side, what you see is AI at play to detect sweet heartening, right? So basically, employees trying to accidentally or purposefully not scanning products at the counter. So deep learning here is trying to track three actions: the worker picking up the object, scanning it, and then dropping it on the other side of the counter. If any of these three actions fail, the system would trigger that as a scan avoidance and summon the supervisor to go solve the problem or address the situation. So leakage is a huge issue with retail. Retailers, as you might have heard already, are trying to embrace AI to increase the satisfaction of shoppers, to minimize leakages or theft in their shops. All right, moving on. So here is a use case that I talk about around using drones for surveillance. As you might have realized, drones have become cheaper, and cities, governments, individuals, insurance companies, they're trying to leverage drones for different use cases, right? So here you're seeing this is all about surveillance of people. On the left side is people behavior in a baseball stadium. On the far right side is surveillance of a parking lot, right? You see the several cars and people and a person moving from a dark shaded region to a brighter region. Having people in malls is fantastic, no problem. But if the car has been sitting in a mall for a couple of weeks, that's a problem. If you have a person jaywalking in the parking lot at 3 a.m. in the morning, that's a problem, right? So all these hints could help someone the right help and make that a better place for retailers. Okay. So here's a use case for smarter city initiatives. On the left side, what you see is ability for AI to detect a near-miss incidents. You got a car, you got a person, and you got a crossway. And if these two objects are moving, touching the crossway, and the pixel differences between the car and person decreases, that's what that could be predicted as a near-miss incident, right? Believe me or not, every traffic light that you will encounter, the stream goes to some video management system. It gets shown up on a CCTV, and there's likelihood that a person is watching it, right? And humans, there was a study done, and humans have this attention of 22 minutes. What that means is after 22 minutes, we either go look at our messages on WhatsApp or Telegram, you name it, right? So we get distracted. But with AI, we can detect problems and then call for help. On the right side is a classic parking lot management. We are trying to look at cars which have double parked. We're trying to look at cars driving out and cars parking in. A lot of insights from this particular video. Maybe the law enforcement want to track down all the illegally parked cars, send them a ticket. Maybe they could also use this information to invest their budget in improving that particular intersection. Maybe the communities were built decades ago before the auto population really blew up, right? So it's time for them to revisit it, broaden the roads, or build better parking lots. Who knows what, right? So a lot of information for cities to improve the life of citizens. So here is a story that I tried to tell in the space of security. Imagine a story in a bank. You have a person with a mask, and then people, with guns, and then there's a shootout out here. And you wouldn't want the bank employee to risk his or her life and call 911. You got to have smarter cameras to detect an argument or a situation and call for help. And on the right side is our efforts to help scanning bags at airports or at facilities. You are trying to detect objects that are harmful, considered harmful for that particular situation. Okay? Lot of possibilities. I believe this is the last slide I have on the use cases before we get into the product. Again, industries are using drones to monitor assets. Clarice is going to show us later today how data from drones can be used to monitor assets on transmission towers. What you see here is drones trying to identify defective solar panels in a solar park. On the left, you see is photovoltaic cells. Once they get through production, the manufacturing unit want to do some sort of quality inspection. Hey, you got scratched wafers, dark spots, bright spots, and a major lot of them is a good one, right? So you need to do quality inspection in industries as well. All right. So what's the dilemma, right? Our customers today have a lot of data. Our customers today are hearing about evolution in hardware with GPUs, evolution in studies like deep learning and machine learning, and they're trying to hire data scientists who can help them find insights from their data, right? Now, the problem is the universities are not churning out as many data scientists as the industry is expected. And not all data scientists are equal either. And our customers are having hiccups trying to jumpstart their transmission of their businesses with AI technologies. Okay. The other part of the story is, let's assume you have data scientists, you have different personas like an image analyst or an application developer. A typical AI model would look like data preparation, installing the right product, data pre-processing, cleansing out the data, right? Trying to make sure there's normalization of data. Finally, you want to train models with that particular data. You want to deploy it, right? Once the models are deployed, you want to monitor the models for its accuracy over a period of time, because these models are as accurate as the data set that was used for training it, right? So there are a lot of processes involved in building an AI solution. And there are different personas: a data scientist, a data officer, an application developer, a system administrator, right? And there are a lot of loose points which could break if not stitched together with the process. So what we have done is our intentions were to lower the barrier of building models for computer vision. We wanted the subject matter experts, the domain experts, to bring in their data and click around to curate their data sets or label their data sets, further click around to train and deploy these models, right? So we have introduced a product called IBM PowerAI Vision that lowers barriers for building computer vision models, right? The idea, the whole purpose is to accelerate the AI journey for customers. Yes, you need a data scientist, but at least you can get 60% of the work done with subject matter experts who understands, for example, the safety concerns in a city. What is a near miss? Why would that happen? When would that happen, right? So these people, security inspectors, have been spending a lot of their time trying to detect and avoid or react to such incidents. And we want to empower them to build AI models for as far as they can go. But data scientists are still required if you want to increase the accuracy of the models beyond a particular threshold, okay? All right, so enough said. I would want to walk you through a demo of our product. Imagine a use case here, a story here, where an insurance writer wants to train a model that will detect a property with a swimming pool or without a swimming pool. And this company has engaged drones. They fly drones across the properties to capture videos of the property or images of the property. And then this insurance writer wants to train a model so that he or she can let AI figure out the properties of the house, and then help write up a insurance claim or a property claim as fast as possible. So here the user dragged and dropped a data set and images of homes with the swimming pool, and the person is going to label it saying, "Hey, machine, these are images of homes with a swimming pool." So what's happening here is what we call here is in deep learning world is called data labeling and supervised learning. We are telling machines like, hey, here are the images with homes, images of homes with a swimming pool, images of homes without a swimming pool. Machines are dumb. We need to teach them. So once you have gone through the process of labeling your data set, you would click a button called Train the Model. And IBM PowerAI Vision starts training a deep learning model that can help identify homes with these two different features. Okay, so what you're seeing here is the model in the phase of training. You see the losses going down. You see the accuracy is going up over a period of time, and the training is happening on machines with the GPUs, graphical processing units, not on CPUs. GPUs accelerate your time to train models. You don't want to be spending months or days to train models. With GPUs, a job, for example, with GPU, a job that took a day could be done in minutes, right? So that's what GPU brings to the table. All right, so the model's trained. Now you would want to deploy the model to validate images or to really infer images, right? So you click a button, the model gets deployed, and you get a RESTful API for application developers to start inferencing data from real world, right? So here I've deployed the model, I'm dragging and dropping an image, and then the system comes back and says, you know what, I found the image you told me to infer is an image with homes, and by the way, I'm accurate by so and so percentage. And there's a heat map that tells the image analyst or the insurance writer saying, hey, why did the machine think this was a house with a swimming pool, right? So there's a big blob on the pool, right? So if I dragged and dropped a home without a swimming pool or something like that, so the system came back and said, yep, this is a house without a swimming pool. Okay. So let's move on. So what you saw so far was called training models for image classification. And I would want to introduce, well, the product does several things. You can train the model for object detection, for image segmentation. I'm going to show you how the model, how the product can be used for image segmentation. Image segmentation is ability for machines to identify the object, classify the object, but also to tell you the pixel location of these objects. Okay. So again, we are going through a process called data labeling. I dragged and dropped a bunch of sample images of Coke bottles, and I'm drawing a non-polygon, multi-polygon, multi-point polygon around this object and saying, hey, here's how a Coke bottle looks like. Okay, and then I would click a button called Train My Model, and the model would try to train a mass CNN model using the Detectron framework to deliver a model for image segmentation. Okay. In this process, I don't know if we have technical people on this call. In this process, the hyperparameters for that particular network are pre-configured. With the help of our research data scientists, we have pre-configured these base models with the optimized hyperparameters so that the models can train faster and the models can infer faster. And we use transfer learning as a technology. Now, our data scientists can come in and change these learning rates because there might be issues with the kind of data, or there might be issues with converging of the models for higher accuracy, right? So data scientist intervention might be required, but not all the time. Okay. All right. So it's time for showpiece now. So you trained the model, and before we train the model, we provide several key statistics on the model. We provide details like total recall precision, IOUs, MMAPs, confusion matrix. These are all pointers for a data scientist or an image analyst to validate the accuracy of the model, to understand the disnormality in the data set so that they can go fix it and retrain it. Remember, training is an iterative process because one would never get high quality of accuracy on their first try. They have to normalize the data. They have to figure out what's wrong with the data so that they can retrain it. Maybe even change hyperparameters. Who knows? Yeah. Yeah, but the point here is we provide all sorts of points of intervention for a data scientist to come in and change these variables so that the models will train for higher accuracy. All right, the model's trained. It's got a 92% accuracy on it. I'm going to validate it by dragging and dropping an image, which was probably not used for training. And I would like to check out the results of image segmentation. Right, so let me quickly pause here for a second. So here the system did find 5 bottles, on which 3 of them were Coke bottles, and it has segmented it, but it has not segmented the bottles for Sprite and Canada Dry, right? Because those were not the bottles we used for training. So this was image segmentation. It's applicable. I mean, medical industry uses this technology to identify tumors, to figure out the sizes of this tumor. Radiologists need to know that information to ensure the efficiency of the prescription. If things are going south, then they can do something different for that patient. Okay. Our manufacturing industry is also trying to use image segmentation, or they would capture these heat signatures or thermal pictures and apply image segmentation to find deformities in the manufactured products. A lot of use cases. So moving on, I would like to talk about our ability to train on smaller data sets. So when we talk to our customers and we talk to them about deep learning and we tell them, you know what, the models are more accurate if you provide us a large amounts of training data sets in thousands and 10,000s, our customers do not have, well, few customers do not have that kind of a data set. For example, here, what you see is a picture of a broken conductor on a power station, on a power tower, basically, okay? You would not find, trust me, one would not find a lot of broken conductors on these power transmission towers, right? But you still got to train a model that can detect broken conductors on transmission towers. So we provide, with the click of a button, we provide ability to augment the data set with simple algorithms, image algorithms. We can rotate it, crop it, deblur it, sharpen it, add some color combination, increase or decrease the contrast, right? So from a particular image, we can generate hundreds of images, right? And that's what satisfies a deep learning model to train up for better accuracies. So data augmentation now becomes a clicking job. All right. So I did talk about base models and using transfer learning for training models. In the product, we ship out a small set of base models so that you can train your models faster. Trust me, nobody likes waiting on a machine while the models are getting trained. We try to accelerate the journey. This is a growing list of base models that we try to deliver. These models are built on publicly shareable data sets. Okay. All right. So I did touch about the advanced metrics that we show once a model is trained. The whole idea here is for a data scientist to understand the hyperparameters. What parameters can be changed so that they can be trained for better performance. To understand the confusion matrix to zero in on images that are kind of skewing the accuracy of the models, and total recall and precision to understand the quality of the model. So all these statistics help our users to zero in on the problem and fix it and retrain the models. Okay. So when we talk to our customers about IBM PowerAI Vision, a click-through tool for training the models, people like it. But data scientists also come back to us saying, "Hey, Sri, how can we use existing models for PowerAI Vision?" Data scientists, as far as I understand, they do not want to waste time waiting on a machine while it is trained. They're expensive. It is not the right job for their skill sets. Number one. Number two is they do not want to be the owners of their inference containers. The models are trained, they're deployed, the data scientists would have a REST API, and they would pass on that REST API for the application developer to start throwing in several images per second for inference. So data scientists do not want to do training and deployment of trained models. They want to build the next generation of models. So what we offer here is bring your own model, and IBM PowerAI Vision can train that model for you. IBM PowerAI Vision can host that model for you so that a data scientist can do something better, something that fits their interest and skills, saving a lot of time for data scientists, improving their efficiency and productivity at work. So here is a story where we say that PowerAI Vision can be trained on a server. This server would be a power system with IBM Power System with a power processor on it and Volta GPUs on them. We recommend at least four GPUs depending on the kind of training you want to do. Let's assume a data center has a server dedicated for training. Now we want to export out that model and deploy it local to a manufacturing floor. You might have a small server with one GPU or without the GPU running on a plant floor, right? We have this ability to train on data center. It's your model. You can deploy that model on a remote server with a little bit of work. You can also deploy that model on a cloud provider, provided you have a GPU or even if you don't have a GPU, we do provide a CPU-based inference, but it all depends on the use case. Is the use case okay with the high latencies on inference with the CPU? But we have the option: train on Power System, deploy it on the cloud, or deploy it on an Intel machine. All right. So I spoke about deploying models on a server class, a resource compute on in a data center or a server. What I'm showing you here is our ability to deploy the models on embedded devices. What is the card? The card you see here is called an FPGA card, Field Programmable Gateway Array. And the story here is around ADAS, Assisted Driving Advanced Systems. You have a camera on the car's dashboard. The camera is picking up the world around the car, and a accelerator like an FPGA on the car is running a trained model that understands people, bikers, motorcycles, cycles, other cars, and hinting the driver about the world around the car. Maybe you're backing up, and there's a car behind you, and the car will help the driver to be careful about it or do something about it. Okay. So there's a challenge where we train the model on a data center, and then we need to deploy it on embedded devices which are not as powerful in terms of accelerators or in terms of disk space or in terms of GPUs or in terms of random access or in terms of memory, right? So we needed to compress these models in a way that it fits the end point, okay? So in IBM PowerAI Vision, we have made this art of compressing, pruning, and optimizing a large model to fit into an endpoint. When we deploy, we ask the question, hey, where do you want to deploy? Is this an FPGA? If it is FPGA, what kind of Xilinx chip do you use? Or is that an NVIDIA TX2 or NVIDIA Nano? So based on those endpoint characteristics of the endpoint, IBM PowerAI Vision compresses the model so that the network, if you imagine the network, we disable a few nodes, we disable a few synapses, but we still try to ensure the accuracy of the model. We emulate the resulting compressed model and make sure that it is decent enough in accuracy before we give it out to an application developer who's got to load it up onto an FPGA or an NVIDIA TX2 devices. Okay. Again, the whole idea here is to lower the barrier of training models, labeling models with less data. Once the models are trained, deploy them on an endpoint of your choice, which could be a server, cloud, or even an embedded devices. We're trying to make sure we're trying to make this journey as clickable as possible. So here are a few use cases where embedded devices are showing up. You have a camera with accelerators on them. Cameras should not be feeding videos to the data center if there's no traffic, if there's no crowd to be monitored, right? So you would want to load up the data only if there's a car or a person in the horizon. There are a lot of startups who are trying to build their own versions of embedded devices. For example, Habana, Critical, i3D. There are a lot of startups who are trying to get into the space of building endpoints based on their accelerated chips. So we are trying to solve one chip at a time. Today we support Xilinx chips, a few particular chips from Xilinx. Alvia U200 is one of them. We also support NVIDIA's Jetson TX2. We are on our way to support Nano, which is more miniature version of TX2. All right, so moving on. I think I might have said this before. So once the model is deployed, we provide a rich set of APIs for an application developer to code up a process around it. PowerAI Vision does not build the solution. PowerAI Vision helps build the best model that would participate, that would be a core element in the solution. An application developer or a system integrator is still required to stitch up that solution. For example, in this case, you got the street cameras picking up the feed, and then an application developer got to understand the feed provider, the protocol, pull that up, call a RESTful API to PowerAI Vision, probably break the video into several frames, call RESTful API for PowerAI Vision, get annotations for each frame, and then figure out what could be that situation. Hey, did the distance between person and the car reduce? Are the cars and people and the person touching the crossway? Are they moving? So the application developer has to build that logic before triggering an alarm. Okay, and we are trying to simplify the life of application developers. They love APIs. They do not want to own deployment environments that would scale. Okay, and PowerAI Vision offloads that responsibility by deploying models trained in its own environment. So if you look at it, we are providing features for several personas: label, data image analysts, or data officers, or data scientists, or application developers, trying to improve their life so that they can focus on what they specialize in, rather than owning jobs that they were not trained for. All right. So roadmap, we are pretty aggressive in releasing our versions. We try to release a version every quarter. We are in our 4th version of the product since we delivered in May of last year. With every release, we try to bring in a differentiator in the marketplace. The most recent release we had was in March, where we introduced image segmentation, our ability to enhance data labeling with data augmentation and whatnot. We want to introduce a lot of cool features like detecting actions from videos, unsupervised learning, 3D image analysis, text recognition and video recognition. And there are other products in the company called IBM Maximo for asset management, Watson IoT for IoT kind of use case. We want to integrate with those products so that our customers would cherish cherish various capabilities from one vendor. All right, so here's my last slide. I have quite a few pointers here on how you could start your journey with PowerAI Vision. If you do a Google search, you will see our content from Marketplace, where you'll see quite a few details about use cases, more oriented towards a business user. But you'd also see a lot of content in our Developer Works portal, where we showcase sample use cases. We sample code from GitHub. We call them code patterns. If you're an application developer, you can just download those Python scripts and try to infer with trained models. Okay. So we also have ability for you to download free trial versions of the product. If you don't have a power system, no problem. You can buy a $3,000 server desktop class from our partner called Raptor. They build workstations or desktops with a Power 9 system, with slots available for you to chip in a T-Force or a GTX 2070. On YouTube, you would see quite a few videos that I have built, a few more use cases than what I had shared in this particular demo. All right, so that's all I had to share for today. If there are any questions, I can take a few now.
Like, Srini, so I guess I'm not sure if this question would be for you or Clarice, but maybe just talk a little bit about POCs that a customer can do, how that might go.
Joe, if you're speaking,
how we
I
help
cannot
them
hear
through
you.
it. Oh, sorry.
Give me a second. Let me dial back in. I'm sorry. Let me just dial back.
Yeah. So can you hear me now, Srini?
So John, if I can answer that question from for clients who are interested in running their own proof of concept, we do have some resources available, and we run some workshops that can go from just use case discovery to trying things out and the main contact for that is cssc@us.ibm.com. And I'll put it in the chat.
Okay, good. Thanks, Clarice.
Joe, I'm back.
Okay. So I think the Clarice answered the question I was asking Srini. So somebody told me that the version of your presentation that I have on the wiki is a little bit different, so I'll have to download that and upload and put a new version out there.
No worries. Yeah, so
okay.
That's not a problem. I will. Yeah, there was a glitch there. I will fix it.
Okay, I can do that. Otherwise, I think maybe we'll move on to Clarice's demo and what she has to show us. And Srini, I know you mentioned that you might have to drop off, so if you do, go ahead, and we'll just carry on.
Thank you, Joe. I will hang on for some time.
Okay, good. So Clarice, I'm just making you the presenter now. And so for everybody that's on the line still, so Clarice is going to go through a demo, actually going through how we, a little PowerAI Vision demo, so talk a little bit more about some use cases. In this particular case, I think it's going to be some utilities use case that she's going to demo.
Can you hear me?
Yes, I can.
Okay, great. All right, so I'll get started. You saw some of this in some of the video clips that Srini showed, but this will take it at a slightly slower pace so that you can see the different pieces that come together for this point-and-click model building. So what I'm demonstrating is the IBM PowerAI Vision. It's the latest version, 1.13, that has some new features that I'll point out as we go through. And I'm basically going to show you 4 different things: how to create a data set, to build a model, how to prepare the data and label what we're trying to predict in our images, how to train the model and tune it, and then show some examples of how to deploy. So let's get started. We can click here or go straight to data sets. What I've done here is uploaded a set of images that we got from the Electric Power Research Institute, also called EPRI. And what this organization does is it brings together utility companies to look at state-of-the-art technologies in their field. And one of the areas that they looked at is to collect a set of images that find defaults in transmission towers. So if you look at the original images that EPRI provided, they categorized images in a lot of different categories with defects. So for example, if you pick these corroded connectors, you'll get a set of images that they provided that show corroded conductors. And if you look at broken ground bounds, you'll get a different set of images. And these are all images where the ground connector to the transmission tower conductor is broken. So there are about 25 categories of these failed images. And what we did is we basically uploaded these images either one folder at a time or all together, and then categorized them into each. So if we uploaded a new image, we would basically assign a category of one of these 25 categories and have a data set that is categorized into these failed parts. So that's our main data set. We have 1,000 images that we used. What we then did is train the model based on those images. To train a model without doing anything else, you would click on Train Model. You would specify, you would take basically all the defaults. So this is an image classification. You would pick the default model that they recommend, and you'd start train. Before starting the training, it's a good idea to see how many GPUs you have available, to make sure you have a GPU available for this training. In this case, I'm running on a PowerAI system with 4 P100 GPUs, and 2 of them are busy because I've already deployed some models on those, and I have models available, 2 out of 4 available for training. So I'll click on Train, and I'm training on this model because it should be fairly quick. It'll go off and schedule the training. It will tell me what default hyperparameters it picked for the model. And you'll see once it starts going, we'll see as it goes through all the steps for training where it reviews the images over and over, it'll give you some progress on that model. So this is the example that it's going. It's already run through 130 out of the 1,500 iterations. And as it's progressing, it's telling me how it's learning, and more importantly, how accurate it's getting. So it started, 50-50 chance that it was guessing the right defect on the part, and now it's up to 80%, 84% accurate and going. So once it completes training, and here it says it's got a minute left, it'll show up in this models category. And if we go to that, we'll see this model that has the training in progress. You'll see 2 other deployed models that I had previously, and you'll see a previously trained model. And now you can see that I only have 1 GPU left available because I've got 1 training and 2 deployed. So let's go back and see if this one's almost done. Not quite. So we'll go back to a previously deployed model that I did. That was the same thing. And it'll give me information on precision and recall of the model. The AI Vision tool is very nice because for every one of these statistics on the model that you created, it will give you a little information box on what the definition of precision is, for example. In this case, it's true positives divided by the number of true positives and false positives. Recall is true positives divided by true positives and false negatives, and so on. And it'll give me that for all of the 25 categories that I'm looking to identify in my energy use case here. It'll also give you the overall precision or accuracy of the model, which is true positives and true negatives across all cases. And you can see here the same chart that I was showing you earlier while the model was training that showed that we got to an 82-83% accurate model. You can also turn on advanced metrics, but we'll look at that in a little bit. So let's go back to our model. Once you've got a model trained, you'll have the option to deploy it. So here's how you deploy the model, and it's a one-click deployment. And what you get as a result is a list of deployed models on what you just trained. So let's go back to the data set, and you can see from our models that 82% was okay, but I want to get higher accuracy. So you can see here I created a model that is 99% accurate. So let me go through the steps of how that was done. Basically, I took the 1,000 images that we had, the initial model, and I used a feature called Augment Data. So Augment Data allows you to create some additional images that you can set up that give you the same images in different contrast, different colors, different direction, cropped, and so on. You can introduce noise in the same images. So if you look down here from that 1,000 set of images that I created, I now have 20,000 more images that I can add to this data set just by taking those same images and adjusting them just by a little bit. So if I do that and I launch that, it'll ask me for the name of the new data set. And I'll have that going on in the background. It's going to create those 10,000 additional data sets, or 20,000 additional data sets. So now if you go back to the data sets, I had already created a data set that had the 20,000 items. And if you look at that one, instead of having maybe 20 to 30 objects per category, I now have closer to 500 to 1,000 objects in each category. So we had looked previously at damage dampers. There's an example of images that are augmented from the original image. So this is the original image, and the ones that have these little stars are variations of that. And you can see slightly different positions, slightly different colors, and so on. So now you have a much richer data set to use, and you can now train against this bigger data set. So if I go back to models, that little one that I started originally is finished. It trained with 80% precision, 82% recall, and at 85% accuracy, and this gives you all the information about that. I can shut down this notification. If I need to go back to it, there's a notification tab that will tell me where I am on some of the work that's going on. And now I can deploy this model as an example. Or I can decide that it's not good enough and go back and create a new model based on my data set that has been augmented. So this is the one that used the 22,000 images instead of the smaller ones, and you can see I have a much better precision and recall result. And if I turn on advanced metrics, I get some additional information that's useful, including, for example, a confusion matrix, which will tell me the true label versus the predicted label and where to find some hotspots that are not working quite as well. So maybe augment those with some additional images, things like that. So that's a confusion matrix. I also have the PR curves that look at precision versus recall by category and so on. So this model I've deployed already. It's called the CT EPRI Images Augmented Model. and now I'm going to go and test it out. So for every machine learning or deep learning project that you do, before you even start the project, you always want to set aside some images that you're never going to let the training process see, so that when you want to really validate how well your model and how accurate your model is, you'll always have a set of images that you're confident the model has never seen. So in this case, I do have a set of images that are sitting on my laptop called test images that the model has never seen. And I can pick, let's see, a porcelain insulator broken, for example, and drop a file to get a result based on this model. And it did find with 99% confidence that the image that I provided to it is a porcelain insulator. This is the heat map that determined what it used to determine that it was broken. And if I look at the original image, I can see a crack here on my insulator, and you can see the heat map overlaid on this image. Let's do another image for fun. Let's see. Let's look for marker balls. I'm going to drag an image, a test image, and here you can see the original image with the marker ball, and the heat map tells you what it used in terms of features built into this deep learning model to determine, with, in this case, 100% confidence that you're looking at a marker ball. So that's basically how you build a model. So we started with a set of images of broken components from the Electrical Power Research Institute. Those were categorized for us, meaning they were labeled. We brought them into the model. We built a training model just by clicking train. Weren't too happy with the original accuracy of the model. Augmented with images of those same images, but slightly changed, and built a new model with better accuracy that we just tested on data that the model, that the training had never seen, just to be sure that we were really measuring correct accuracy. So the APIs for running this model that we're now satisfied with could go into apps, could go into other workflows, so that when inspectors come in, not only do they have their eyes to rely on, they could rely on drone information that tells them where to look for defects, and save time and actually safety is better for them as well, because they're not needlessly taking actions climbing up the transmission towers. If we have a little bit of time, I'll show you a couple more things on going back to the data sets. You'll notice here that I also have a data set that, if you look into the data sets itself, these are not categorized, the images are not categorized in categories themselves, but in fact they're labeled as objects. And so I have here, if you pull up an image, you'll see I have rusty bolts labeled. If you look at a different image, I've labeled hardware components and rusty bolts and insulators. So this is, instead of a classification problem that I'm solving, it's an object detection problem that I'm solving. And in fact, when we did this model, we did not have the features that let you map the object better. We just had boxes, bounding boxes. So we intend to redo this model now with, instead of bounding boxes for insulators, we're actually going to draw polygons on the individual insulators, and that'll improve the object detection accuracy of our model. So this set of models, that is a object detection model, I trained that model and got a model that is deployed, and I'll show you how that works. I uploaded a video, and I asked it to detect the objects on my video, and here you can start and see what the outcome is for that. So image classification and object detection are slightly different. So this is basically recognizing the pieces of the transmission tower that I was looking for. In this case, it was a hardware, insulators, and rusty bolts and dampers. So just four objects. And what this does is it takes the images frame by frame and runs it through the inference of the model I created, which is not particularly accurate. We're going to redo it with object detection here instead of bounding boxes for insulators, for example. So that's an example of object detection and another way to use AI Vision with the point and click features. So that concludes the demo. I'll stop for any questions that you may have, and let me know, and I'll work around the model itself for you to take a look at.
Okay. I think it's important to note here, Clarice, you went through and you augmented your data, you improved the accuracy. But I think in real life here, getting the accuracy up is what's important, and you tend to train your model many times, as you go through production or whatever, and you find things where, it failed because of this or that, and you go back and you train a new model, or you improve the training on the model for some reason. That's one of the things that takes time, and getting it done faster saves that time and makes you more productive. So, this is great software, but IBM also brings together hardware for that reason, with the GPUs and the special features that IBM has in their hardware, which we don't really not going into all in this particular webinar, but they help with that training, and I think it also makes it so businesses be more productive to get all those models out.
Yeah. In fact, sometimes I just brought up just a regular window on our system, and what we'll look at, for example, is how busy the GPU is as we're working through the models. So, agree. Having the resources behind this to make it go fast is really the critical piece to get through to the right accuracy of the models that you need.
Right. So there was a question here that somebody typed in just about the usage of the GPUs, Clarice, when you're actually doing that. So your system had 4. When you trained your model, you used 1. Do we spread? Do we use more than 1 GPU, and can you spread it across even more than 4 GPUs across different systems? So
for the current PowerAI Vision model, every activity is with a single GPU. And so you're multitasking, doing different things with the different GPUs. With the Watson Machine Learning Accelerator, we've got something called DDL, which is Distributed Deep Learning, which lets you train across multiple GPUs. And that's for basically the more advanced type of training and modeling.
Right. And also, I kind of already talked about this a little bit on the Q&A session. When you train the model and everything, you're using these GPUs, and you want to do that in as fast as possible. When you actually deploy the model, though, you don't need those GPUs to deploy the model.
No,
maybe you can elaborate on that,
were models that were deployed on the same server just because it's convenient. But yes, most times being able to deploy it on maybe a cheaper GPU or an FPGA or other systems at the edge is the high strength V100 GPU is really tuned for the training piece.
Right. Okay, so I'm just looking through here to see. So there's a question, is there any plan to include the distributed deep learning and the large model support function to the PowerAI Vision?
That will be a question for Srini offline because I don't know. I don't think it showed up on his roadmap explicitly.
So, all right, I'm sorry. So was the question to include DDL and LMS?
Yes.
Not yet. Not yet. We are working on it. There are a few other differentiating features that we need to tackle before we get to DDL and LMS. What we have done is when we train, we ensure that all the resources on the GPU are dedicated for the training job. So we make sure that you're optimizing your training jobs on that single GPU. But yes, we plan to extend multiple GPUs for training, but that's coming. Not yet. Maybe end of this year or early next year.
Good. Okay, and when you actually get a model to deploy queries, can you talk about somebody was asking about the format of the model. Is this a proprietary kind of model? Do you have the option of deploying it? And you said we can do it in other different ways, right, on the edge or FPGAs and such.
Yeah, sorry, I lost. I mean, I thought I think there are several questions in that one question. When you talk about models, we provide different kind of frameworks: Caffe, GoogleNet, Detectron, different kind of networks, even TinyYellow, different kind of networks, fast RCN, mask RCN, okay. Now, that's the kind of framework, that's the kind of models or frameworks that we give out once you train a model. Number two, when you want to run that on a different server, no problem. We provide a small container that is pre-built with all the frameworks and versions I just told you. All you need to do is import the model that you trained on the server. But when it comes to embedded edge devices like NVIDIA Jetson TX2, we follow the same process. We provide a container built for this ARM core devices.
Right, and I'm showing the export model piece, and it'll save a zip file to your system, and then you can upload it this way with the import zip file. So that's how you can move training models around as you're actively training them and need to move to a different system, for example.
All right, so question on the chat. Deepak asked, hey, can I use multiple GPUs in AC92? The answer is no today. One GPU for training, but you can use the same GPU for hosting several deployed models. It's only for training that we lock up a GPU. We do not do distributed deep learning.
Okay, so that looks like, okay, so Rex was asking if we have a PowerAI Vision demo for a medical image. So, you talked briefly, you mentioned, like looking at scans for cancer or whatever, I think, Srini.
Right.
Do we have anything out there, like a YouTube video or something like that?
We have a radiology example. We've got a breast cancer detection example. We've got skin melanoma examples, and I'm thinking there's at least one more on blood type. Yeah, blood diseases. So
well, we also got the bug bites, as simple as we also got something called bug bites.
Bug bites, yep.
Okay, so several different kinds of things out there for people to look at.
Yeah, almost every industry has a use case and examples that match vision models in those industries.
Mm-hmm. So there's a question on the ability to use crowdsourcing to train a model where you have many trainers. I'm not sure. I mean, you could have people provide multiple images, but I'm not sure you could have multiple trainers for the model, or maybe there's a way to do that.
So there's a lot of labeling support that is done here. One example, for example, is with videos. If you wanted to label objects, you can capture frames. So you could have a lot of people working on this differently. You can auto capture frames as well, and assign different people to do different labeling pieces. But it would still be, assigned users within that PowerAI Vision product. I don't think it would be it wouldn't be crowdsourced from that perspective.
Okay. And there's links in Srini's presentation at the end of that he shared, and I'll make sure that those are on the wiki version. If it's different and they're not there, I'll fix that up.
Yeah, Joe, I sent you the latest version, so go for it.
Okay, super. Thanks, Srini. So Deepak has asked a question about HA working. If the server that's doing PowerAI Vision goes off, is there a way to resume where it started? Like if your training stopped in the middle?
No, it's not available. We tried. Yeah, it's not available in the product today.
Okay. And I think that's it.
So we do provide. Well, Deepak, you're from IBM. I can take this offline as well. So we do provide a way to interrupt a training job. Let's say a training job takes 2 hours, but you want to pause it. You can pause it, or you can just terminate the training job right there. You still get a model that was trained so far.
For however many iterations it's gone through and whatever the accuracy is at that time.
Right.
Yeah.
Right. So
okay.
This is not, HA for computer vision is how do you scale inference APIs, okay? It is not a session management as we would see, as you would see in a banking transaction, okay? So we do provide ability to host inferencing, host the models. You could get several APIs, but we do not have a HA in front of them.
Okay.
Okay. All right, Deepak, let me know if you have questions. I can answer you via an email or same time chat.
Good. Okay, so I want to thank you, Srini and Clarice. This has been a great session, and I appreciate all you did in going through the demos and everything for us. And for everybody else, I want to thank you. I hope to see you at TechU. Let me know if you're there. And otherwise, I'll have the things for the May webinar sent out sometime, hopefully in the next couple of weeks. Maybe I can get it out during TechU next week. And I can't even remember the topic now off the top of my head. So you'll just have to wait for the invite. But hope to see you on that one, and have a great month.
Thank you.
Thanks. Bye.
Bye.